Hello class. This video I want to rehash inductive effects because we're looking at two types or two reasons why that can explain chemical shifts. And inductive effects is one and the other is anisotropy. Now with inductive effects, you can see this chart here showing us that as the more electronegative groups, so we have a bromine, a chlorine, this oxygen and fluorine, you can see that the chemical shifts are getting larger. And that is in fact due to the electronegativities of these elements pulling electron density away from the hydrogens. So in essence, we are deshielding these hydrogens to a greater extent as we go down this table. Excuse me. So inductive effects, more electronegative the atom, it's going to cause a greater chemical shift for the protons that are nearby. Now we can also see in this example where our R group here is alkyl and we have our predicted chemical shift around 0.9 ppms. If we add a chlorine, we see that it's 3.1, but look at this. What if we have two chlorines attached? Then it is even further downfilled. So when we continue to add additional electronegative elements to the molecule, the hydrogens are going to be deshielded, and so essentially it's additive. So you could have put, let's say, instead of having, let's see here, instead of a chlorine right there, if you would have had put that a fluorine instead, you would still see the same thing. It would just get further and further downfilled. And if you would have had something like this, right, so that would even be further downfilled than 5.3 parts per million. So it's an additive process. Another aspect to consider when we're looking at inductive effects is what if I have a molecule, let's do that in black. We have a molecule here, okay, and there's our hydrogen. Let's see here, let's change that. Okay, so let's just look at one of these. There's a hydrogen here, here, here. Okay. Now let's say we put a very electronegative atom over here. Okay. So what we are looking at is distance from the electronegative atom. So we know inductive effects is going to pull electron density through these sigma bonds all the way towards the fluorine. But this hydrogen right here is going to feel that inductive effect the least. And this one right here is going to feel the inductive effect the most because it's closest to the fluorine atom. So when we go and predict chemical shifts, let's say we have three signals here, and if we labeled these HB, HA, and HC, we would predict and be correct in saying, hey, HA is closest to the fluorine, so it should be right. It should be the furthest downfilled, and then so forth. Okay. So this HC is still going to be affected by the fluorine's electronegativity. Okay, the second aspect that we need to talk about is the magnetic anisotropy. And this affects the chemical shifts. That's the second factor that we need to look at. Okay. So this right here, this effect is responsible for the chemical shifts in benzene and alkenes and alkynes. Because what's interesting is if we compare the molecule that we've been looking at, the fluorine next to the carbon, right? We're looking at the chemical shift for that, and we said it's around 4.2. That's because that carbon right here is attached to the fluorine, a very electronegative atom. But when we look at benzene, we see that these 6 hydrogens have a chemical shift about 7.3, which is kind of weird because look at the atom that it's attached to. They're carbons. Carbons aren't very electronegative. So why are these hydrogens so deshielded from carbon? It has to do with this concept of magnetic anisotropy, and it happens when you have pi systems, double bonds and triple bonds. So the inductive effect cannot and does not explain why these hydrogens on the benzene are so far downfield. So let's get into the explanation of it. So you see in this diagram here, the black and white spheres, that's the benzene ring. And benzene has a lot of pi electrons. And those pi electrons look like that they're occupied in these donuts above and below the benzene molecule. And this is called a conjugated pi system, which we will learn about what that means in future chapters. But we have a conjugated pi system here. And when you take benzene and put it in an external magnetic field, the electrons start moving in a circular movement shown by these dotted arrows right here. Okay? And when the electrons start spinning in that circular fashion, you're going to generate a ring current. And so we generate these magnetic fields right here shown in the blue arrows. Okay? And so we see that the magnetic fields, let's just start here at my pointer. Do you see how they're going up and then curving and going down into the center of the ring? And it just keeps going like this, right? You see that? So that's what happens. Now what's interesting here is paying attention to the arrows, okay? The blue arrows. Let's see here. Okay, let's look at it on this slide right here. So what happens is, do you see how we have an external magnetic field? Right here, there's our external magnetic field. And then we have basically it's the local magnetic field. Do you see how that at that point in time, or that point, that is in line with the external magnetic field? So in the previous video, previous videos, I talked about how that when you take a simple alkane and you place that into an external magnetic field, the protons are going to have a local magnetic field that is in opposition to the external magnetic field. And I said that's always the case. And so now when you sum up these two forces, you're going to get the B effective. Remember that? Well, I kind of misspoke. That applies for alkanes. In alkenes, on the other hand, it is the opposite. That local magnetic field is aligned with the external magnetic field. And so what's going to happen is on the energy diagram here, if we look at benzene right here, we would expect the difference between the alpha and the beta state to be very, very small because the carbon atom isn't very electronegative. But the anisotropy here shows us, hey, this is being added to the external magnetic field. So what it actually looks like is it's much larger, that gap is much larger between the alpha and the beta state than what we would predict based off of just electronegativities. Okay, so do you see how the hydrogens right here on the outside of the benzene ring are outside of the ring, and they're in line with that magnetic field line. Whereas these arrows going down on the inside, can't really see my pen there very well, right? The magnetic field lines going down into the ring don't touch the hydrogens. Okay, so that's kind of what we're envisioning here. These magnetic lines are touching the hydrogens, whereas these are not. Okay, so that's why we see such a large chemical shift around 7 or 8. It's because of the magnetic anisotropy making this change of energy of the spin state so much larger than what we would predict. Now we see the same concept when we're looking at typical alkenes. So we have our alkene right there in the center. And when you take an alkene, stick it into an external magnetic field, we start getting the electrons moving in a circular fashion. That generates a ring current. And do we see it's kind of the same thing with the benzene ring? These hydrogens on the outside are in line with the magnetic fields pointing in the up direction, which is in the same orientation as the external magnetic field, which puts these alkane hydrogens around 5 ppm. These are also called vinylic protons, because that's the definition of the vinyl group attached to the double bond there. So that explains why these alkenes in benzene and in a typical alkene is so far downfield when you wouldn't think so at the start. Now, what do you think about the aldehydes? Aldehydes also experience massive deshielding. So this hydrogen right there experiences massive deshielding due to the magnetic anisotropy. And so that proton, or the aldehyde proton, is very, very distinct. It has a chemical shift around 9 to 10 ppms. So if you ever have a signal with a chemical shift of 9 to 10 ppms, it's indicative that you have a aldehyde. It's very, very unique. So you can always count. Now I got to choose my words carefully here. It's very likely, very, very likely that you have an aldehyde. If you have signal around 7 to 8 ppm, it's a really good chance that you have a benzene ring in your molecule. It's not a guarantee, but a high probability. Okay. What do you think about alkynes? They have pi bonds as well, right? If we look at a simple alkyne right here, we have a lot of pi electrons right there. And it only has a chemical shift of 2.4. So that's kind of a shock at first. Like, why is a benzene ring around 7 and alkenes are around 5, and an aldehyde is around 9 to 10. Why is this so has such a, or be more specific, this hydrogen here not have such a large chemical shift? Well, it all has to do with the fact that we look at the magnetic field lines, and it has to do with the fact that the pi orbitals here are cylindrical. There's a lot of symmetry here. Okay? And when you take these molecules to stick them into the magnetic field, look at the lines here in blue. Okay? So you have some of them going up, and then you have some of them going down. Okay? So what's happening here is that it's generating what's called a shield cone. So let's go to the whiteboard here. Right. So if we backtrack and look at a alkene for a moment, okay, and we know that the field lines go like this, okay, right, something like that. What's happening here is you're going to generate what's called that cone. We have what's called a shield cone right there. And on the inside of that alkene, this is all shielding. Right? And so the hydrogens on the outside now are deshielded. But when you look at a alkyne, I'm going to draw it this way. It generates a cone that kind of looks more like this. That's not the best way there. Okay. And so where's that hydrogen on the alkyne? Do you see how the hydrogen itself is in the shielding cone? Whereas on the alkene, the hydrogen is on the outside of the shielding cone. So that when you look at the field lines here, this hydrogen right there, you see at these two field lines are in a line with the magnetic field, external magnetic field. But then these two right here are in opposition to the external field. So because you have these two magnetic lines in competition with one another, it's not going to deshield it as much as we would have expected. Because when you look back here, these down arrows right here don't influence the hydrogens because those blue arrows are nowhere near the outer hydrogens. Okay. Okay, so so if I take this image here, our shielding cone would be like that. Okay. So that explains why the chemical shifts for alkyne hydrogens are not as large. And this concept of deshielding through magnetic anisotropy also influences distance as well. So what we have here is a hydrogen directly attached to the benzene ring. And so the anisotropy is going to have a greater effect on that hydrogen because it's within those magnetic field lines. But as you go one carbon away, do you see how that is a methylene hydrogen? and methylene hydrogens should have a chemical shift around 0.9 to 1.4. But it is that carbon is attached directly to a benzene ring. So the magnetic anisotropy still has an effect on that guy. And the molecular or magnetic anisotropy has an effect on that guy. But you pay attention to the chemical shifts. It has a lesser effect as you get further and further away from the benzene ring, which is influencing the shielding effect here that we're seeing. All right, so this right here, this slide right here is analogous to the example that I did up. Let's see here, right here. All right. So you could take this same example right here, replace the fluorine with a benzene ring, and you'd have the same concept here. You have the same outline or the same pattern. Okay. If you have any questions or concerns, please reach out. I'll be more than happy.